Welcome to this explainer. Today, we're taking a behind-the-scenes tour of what is essentially an AI factory assembly line. We all interact with models like ChatGPT pretty much every day, right? But how do they actually process our prompts and spit out those amazingly human-like responses? Well, we're going to look right under the hood to see the architecture, the training, and the controls that actually make large language models tick.
Okay, so it's kind of wild to think about, but no matter how smart or creative or empathetic these tools might seem, fundamentally, they're just playing a massively complex game of fill in the blank. I mean, if you give the model the phrase, "the cat sat on the," it uses probabilities to guess that the next word should probably be met. But how it actually arrives at that guess, that's where the real magic happens.
So here's our roadmap for today's explainer. We'll start with translating text to tokens, explore the transformer architecture, and then look at pre-training the brain. After that, we'll dive into alignment with RLHF and DPO, the rise of thinking models, and finally how developers actually control the output.
Let's kick things off with step 1, translating text to tokens, which is basically breaking language into Lego bricks.
Before a computer can even read language, it has to chop it up into numerical pieces. Now, treating every single letter as its own unit, way too computationally expensive. But using full words creates this gigantic, unmanageable dictionary that totally breaks down when it sees a new or rare word. So, modern systems use something called byte pair encoding, or BPE. It's this absolutely brilliant method that treats language just like Lego bricks. It takes a word like encoding and breaks it into smaller, reusable chunks like encode and ing. This helps the model generalize and actually understand grammar.
The tokenizer goes through a very literal step-by-step loop. It starts with your basic characters, scans a massive corpus of text for the most frequent adjacent pairs, and just merges them together. It repeats this over and over until it hits a target vocabulary size. Through this compression, one token usually ends up equaling about 4 characters, which is roughly 3/4 of a standard English word.
Moving right along to step 2, the transformer architecture, the true engine of modern AI.
Introduced back in a landmark 2017 paper, the transformer is the revolutionary neural network that processes all those tokens. If we look at how it evolved, there are 3 main families, but the decoder-only stack is the one that completely won the conversational AI race. Why? Mainly because it uses something called causal masking. This is a mechanism that strictly prevents the model from peeking ahead at future tokens. It literally forces the model to auto-regressively predict the very next token sequentially, which turns out to be absolutely perfect for generating interactive back-and-forth dialogue.
But wait, how does it actually understand the context of your prompt? Well, the transformer uses this fascinating mechanism called self-attention. Because the model technically sees your text as an unordered bag of words, it has to inject mathematical positional information just to keep the word order straight. Then, self-attention calculates the relationships between every single word. So if you type, "the pizza came out of the oven and it tasted good," self-attention is what helps the model realize that it refers back to the pizza and not the oven. It connects those far-apart concepts almost instantly.
Which brings us to step 3, pre-training the brain. This is where it learns the rules of human communication. This is the phase where we take our shiny new transformer engine and just expose it to the world. The model reads incredibly vast, uncurated datasets. We're talking literature, news, millions of lines of code. By maximizing something called log likelihood, modern models evaluate the probability of nearly 200,000 possible vocabulary tokens for every single step. Just think about that scale for a second. Out of roughly 199,997 options, it guesses the next word, tweaks its internal weights, and slowly, painstakingly maps out the rules of human grammar and semantic nuance.
But here is the really crucial point. A model fresh out of pre-training is basically just a raw autocomplete engine. If it learned from the open internet, predicting the next word absolutely does not mean the model will be helpful or harmless or polite. It might spit out toxic garbage or go off on endless weird tangents. And that brings us to the next massive hurdle in the factory line.
Step 4, alignment through RLHF and DPO, or as I like to call it, teaching the AI good manners.
To turn that chaotic autocomplete engine into a polished assistant you'd actually want to use, we have to align its behavior. And there's been a massive shift in how we do this. Traditionally, developers used RLHF. That's the technique that originally made ChatGPT famous. It relies on humans physically ranking answers to train a separate reward model via reinforcement learning. And it works, but it's insanely expensive and mathematically pretty unstable. So now the industry is quickly shifting to DPO. DPO is this newer breakthrough that gets you the exact same alignment but completely eliminates that middleman reward model. It optimizes the AI directly based on human preference data. It's a total game changer because it's much faster and cheaper.
Moving to step 5, the rise of thinking models and verifiable reinforcement learning.
So what if we want the AI to go beyond just being politely helpful? What if we want it to solve incredibly complex math? That is where we get models like OpenAI's O-Series or DeepSeek's R1. Instead of relying on a human reviewer to say, yeah, I like this answer better, these models learn to actually reason by practicing tasks with objectively verifiable answers. Using verifiable reinforcement learning, the AI will write some code, and an automated sandbox compiler will just run it. If the code passes, the AI gets a positive reward. If it crashes, negative reward. The model learns hardcore logic and chain-of-thought reasoning entirely through objective trial and error. No human grading required.
Finally, step 6, controlling the output. Let's look at the inference dashboard.
Okay, so our model is fully trained, aligned, and deployed. We've reached the inference stage, which is the actual generation of the text that streams across your screen. When the AI is generating, developers have these specific dials they can tweak to control the flavor of the output. Temperature scales the raw probabilities. Turn it down, and the AI is super conservative and factual. Turn it way up, and it gets wildly creative and random. Top K strictly limits the AI to only even consider the top set number of most likely words, say the top 50. And Top P dynamically limits the vocabulary based on a cumulative probability threshold, essentially adapting to how confident the model is at that exact millisecond.
And you know how the text usually types out super fast, instead of you staring at a loading screen forever? That's thanks to a brilliant memory trick called KV caching. Because generating text autoregressively means predicting one single word at a time, the model normally has to recalculate the entire previous paragraph for every single new word. KV caching just stores the intermediate mathematical states of those previous words, drastically speeding up the generation process so that text just flies onto your screen in real time.
It's truly incredible, isn't it? Seeing how a simple next word predictor gets molded, trained, and optimized into a full-blown reasoning engine. We have gone from just predicting Matt after the cat's head on the to models that objectively verify their own software code in a sandbox. But as these automated, verifiable rewards take over the hard logic stuff, it leaves us with a really fascinating question. What highly subjective human tasks will we actually need to align them with tomorrow? Thanks for joining me on this explainer of the AI assembly line. Keep questioning and keep learning.